Okay, mic check. Let's see if you guys can hear me. There's still a few minutes left until the start of the actual event on Discord, but I decided to just start streaming to see if everything works. So please tell me if you can hear me. You should be able to hear me, I think. Yeah, looks like it. Let me switch. Oh, okay, yep, hello. Let's see. Oh, okay, audio fine, perfect. Thanks, PT. And nice to see you here. Mic is good, awesome. All right, yeah, we still have a few minutes. I don't really have anything prepared for those few minutes, so it's still just waiting. So if you have something to do, you can safely step away from the screen. You will not miss anything until like 9 p.m. 9 p.m. European time, like Central European time. Might be a different time for you if you're somewhere else. Yeah. I'm already in the voice chat and on Discord, but for now I muted myself and I muted the Discord so that it doesn't interfere, because people are talking about a different thing there right now. Yeah, I'm really curious how this will go. I hope I'll be able to make this topic interesting, and I hope I'll be able to say something of value. But I guess we'll see. Oops, not this screen. I'll turn off the camera now because it won't really be of any use during the stream. People on Discord won't see me. Only the stuff on the screen is really important. Yeah, I'll also turn this off. And yeah, and we wait 5 more minutes. I saw that Nerd Alert mentioned Nero the Fogger. He's a guy that's been in MC Toon's Discord some time ago and recently in FTFE's Discord. He's well, the simplest way to put it is probably a relativity denier. So actually, I watched one of his videos where he talks about why he doesn't believe in relativity, and he actually inspired me a bit to make a video about relativity. So I was planning some a video or maybe a series of videos about an introduction to relativity. So I actually made a bit of a script already. But before I actually recorded anything, because I also wanted to make some animations, stuff like that, and this always takes me a long time. So before I actually managed to do any of that, basically I got invited on Globe Gangsters to give a talk about general relativity, because basically we were exchanging information about who knows about what, stuff like this. So I mentioned that I actually have I'm a physicist by education. I'm not a PhD, only an MSc, but still, and I was specializing in basically the maths of general relativity. So then I got a request to talk about it, and because I love to talk about relativity, I gladly accepted, and then basically here we are. So I hope this is going to be interesting. Yeah, what I'm going to be saying is mostly the stuff I was planning for the video, but not quite. But maybe the live stream is actually a better form. I mean, it definitely saves me a lot of editing, so it's much easier, and it allows for some interaction, so people may ask questions during the event, so that might be useful. Yeah, so we'll see how this turns out. If this is interesting, I'll gladly continue and make this into some sort of a series. So make part 2, maybe part 3, depending on how many parts it takes to say what I have to say. Okay, let me now turn on the sound on Discord to see if we're starting, maybe.
A federal watch list? I'm pretty sure that's not a thing.
Let's see. Okay, you guys
On a
should
federal
be
what list?
hearing
Federal
this
watch
as well.
list?
I mean, there are watch lists for suspected terrorists.
But it's not like they
I don't know.
publish, let you know when they're watching you, right? Doesn't that defeat the whole purpose?
Kind of. Yeah, I don't think that that's easily done. A thing that's easily done. I mean, watch lists are kind of a weird thing.
Oh, okay, I see they are still talking about something else. I'll unmute myself at like 9 or something, so in 2 minutes basically. And we'll see if we can start. I have a lot of screens to juggle to figure out what's happening. I have a Discord, well, not physical screens, like I have just 2 physical screens, but virtual desktops. So I have Discord and live chat from this stream on one desktop. I have some notes on another desktop. I have the stuff you see on another desktop. Inkscape, which is not this one because this is still like LibreOffice Impress, but I also have Inkscape on another desktop, so there is some stuff. And I'll have to juggle it somehow. Oh yeah, OBS on another desktop. Okay, let's see.
Yeah, but at that point they're aligned with all the focuses lie on the same direction. So I feel
Yeah. Yeah, it's a little bit. Yeah, if you want to say that, yeah.
I do want to say that. That's correct. Anyway, so
Okay.
I think we're starting the thing right now, right?
Yeah, probably soon. Yeah, just wanted to give you a heads up. By the way, I'm already streaming, so if any of you are watching on my channel, it should already be working, but probably it will be easier to just watch here. It will be real time. And yeah, just let me know when we should start.
Oh, you have the floor.
Yeah, whenever you're ready, sir.
Yeah, should we start already? Okay, yeah, it's like, it's exactly time right now, according to my clock. Okay, let me share my screen because this, I guess, will be useful. Wait, it's not this, it's this. And apparently it won't have such a good resolution on Discord, but hopefully it will be good enough. Okay, I hope you can see what I'm sharing now. So, hello.
Yes, we can.
Awesome. So hello. Yep. I'm Bart. I go by Science It Out on YouTube and Discord servers. And yeah, I've been invited to give this talk about relativity. So yeah, let's start. This will be an introduction. So I'll try to keep it quite simple. It was supposed, but yeah, maybe let's go to that. Yeah. So some notes first. This was supposed. Wait. Okay. This worked. Something weird happened. But anyway, yeah, this was supposed to be about GR, but General Relativity. But when preparing this, I realized I have quite a lot to say about Special Relativity first, because you can't really meaningfully talk about General Relativity without talking about Special Relativity first. And since I didn't want to assume that everyone's already familiar with special relativity, I decided to kind of give an introduction to that, and it turned out to be quite a big introduction. So I'm pretty sure that we won't have time today to actually reach general relativity, so we will be in the realm of special relativity mostly. And I'm not even sure if we'll have time to say everything I have to say about special relativity, but yeah, we'll see. If we don't manage to get to general relativity, there might be part 2. I mean, this will depend on whether what I'm saying is actually interesting, because I mean, there is no point of continuing if I'm too boring. But I hope it will be fine. And yeah, so general relativity uses some advanced maths. Special relativity also is a mathematical theory, but it doesn't use such advanced maths. But anyway, I will actually try to use as little maths as possible. I want to give you guys an intuition how this works, not exactly maybe the whole maths behind it. I mean, I'm still open to talking about maths if there are questions, if you guys want to go more into depth about something. But basically, I will be focusing on more of a, let's say, qualitative view than quantitative. Let me see. Okay, something is okay. There is a chat here. Oh no. Okay, this is just the other channel. Never mind. Okay, yeah, and last point. If you have questions, feel free to ask. I mean, I like to hear that. I mean, this will be valuable feedback if something is unclear, if something can be said better. If you think I'm saying something wrong, of course, also let me know. I'll try to correct myself, and hopefully I won't say anything false today. Okay, so let's continue. Yeah, so relativity. There are a few ways to introduce relativity. So basically, historically, the way relativity came to be was, well, people made some experiments that seemed to point towards speed of light being constant. So from there, basically, the Lorentz transformation was derived and the whole theory of relativity was built. But actually, some smart people, among them mostly Minkowski, noticed that this Lorentz transformation actually corresponds to some geometrical structure. And this geometrical structure turned out to be it could be further generalized, as it turned out. And actually this then led to general relativity. So today I won't be introducing relativity from the historical point of view. I won't be going with this chronologically and from the side from which it got discovered, but I'll actually use an approach like starting from the geometry. And this is an approach that my professor used when I was at the university. So I found it really interesting, and I found this approach to make relativity quite intuitive. So that's like my main hope from this, that basically you will be able to perceive, you will be able to see how relativity is actually not as counterintuitive as one might think, that it's actually in some aspects pretty intuitive. But yeah, I guess we'll see if I succeed. All right, so events. Let's start actually going into the physics. So events are the most basic notion in relativity. So basically, what is an event? An event is something that is happening somewhere and at some moment in time. So if something has a well-defined point in space where it's happening and a well-defined point in time, that's an event. And we need 4 numbers to refer to an event. So basically, how can we refer to a specific event? We need to somehow describe where it happens in space. That can be described using 3 numbers because we live in a 3-dimensional space. So for example, we could use latitude, longitude, and elevation. That would work mostly for Earth, but not only for Earth, really, because elevation could be pretty huge. We could use some kind of a Cartesian coordinate system. It could be centered at the Earth, it could be centered at the Sun, it could be centered at the center of the galaxy. It doesn't really matter. What matters is that whatever we do, 3 numbers are sufficient to describe a point in space. And we need the fourth number, time. So the way we describe time, like dates, times, stuff like this, they usually consist of more numbers than one, but they can be reduced to a single number. For example, in computer systems, a common number used to describe time is Unix timestamp. That's a single number that describes a point in time. Astronomers use Julian dates, for example. That's also a single number. That's the number of days that passed from some specified point in time. So there are ways to reduce time to a single number. And then when we have four numbers, we can describe an event. And actually, everything in the universe happens somewhere and at some point in time. So we can think of the whole universe as basically composed of an infinite number of events. Basically, we can think of space and time as a whole space-time that can where we can refer to any point using four numbers. So we have a four-dimensional object that we can think of as well, basically what the whole universe is. So that's kind of the background, the basic model used by relativity. Let me see if... Okay, because I'm seeing... Okay, never mind. Yeah, I'm seeing some chat messages popping sometimes, and I was wondering what that is because I never really streamed on Discord before, but from what I see, it's nothing too important right now. Okay. So now that we know we're talking about space-time and it's four-dimensional, let's jump to do some diagrams. I hope that you will be able to see this. Okay, so let's assume this this blank slate here is our spacetime, and we want to introduce some coordinates on it. So basically, as I said, space and time, like four numbers, but well, I can't really draw in four dimensions, right? And I don't think anybody really is able to draw in four dimensions. So for purposes of illustrations, space-time is usually reduced to just two dimensions. So one dimension of time and one dimension of space. So for example, we can have a time axis. Do you guys still see what I'm streaming when I'm focused on another window? Because I see a message that, okay, maybe it's just a preview that's, okay, it's just a preview that's paused, okay. So we can have a time axis and then we can have a space axis like t and x. So this, if you're not familiar with relativity, this might look a bit weird to you because usually when you're doing like graphs of, I don't know, position over time or speed over time, then time is usually the horizontal axis and the other quantity is the vertical axis. But usually in space-time diagrams, time is being used as a vertical axis, and then horizontal axis is basically position in space. So we need to remember that this single x-axis, which here is one-dimensional, actually represents 3 dimensions of space, but it would be impossible to draw. Fortunately, for most things, it's not necessary to have all 4 dimensions, and even 3 dimensions are rarely that important. Most of the important things can be shown using only 2 dimensions, so that's pretty fortunate. Okay, let me consult my notes. If I said what I wanted to say. Oh, okay. One more note, because yeah, I'm pretty sure someone watching this, especially from the flat earth side, will raise that, hey, diagrams aren't reality and math isn't reality and stuff like this. To which I'll just quickly say that, yes, sure, diagrams aren't reality, and what I'm showing here on the diagrams won't be reality, but diagrams can be useful to illustrate stuff happening in reality and gaining some insight into how reality works, kind of similar to how maps can allow us to gain some insight about the structure layout of some area of land, for example. So yeah. Okay, so we have a diagram, we have a time axis and we have a space axis. Now, important thing, like when we introduce the coordinates, they already define some kind of a frame of reference, which means they are already relative to some observer. This might not be so obvious with time, but it should be pretty obvious with space. because what's, for example, a single coordinate in space for me when I'm sitting at the train station, for example, I would say that the bench on the train station is not moving. It's still at the same coordinates in space. While if someone is on the train passing through the station and they are moving, to them, this bench is moving. They had it ahead of them and then they have it behind them. So if they introduce some coordinates relative to themselves, the spatial coordinates of the bench will be changing in time. So just because I'm setting some kind of axis here, that already implies an observer. So let's call the observer whose coordinates those are the yellow observer, because those are the yellow axis. There will be more colors in the future, so this will be the yellow observer. So let's consider what an object at rest relative to the yellow observer would look like in such a diagram. So, for example, let's say it is somewhere here. So time equals 0 will be like here. Can you see my mouse cursor? Because I'm not sure if this is visible on Discord.
Yes, we can.
Okay, awesome. So yeah, time equals 0 will be here. So let's say there is some object that was here at time equals 0. And if it's at rest, then it will still be at the same x coordinate at some different time, and at some different time, and at some different time. So the way this will look like, object at rest will look something like this. It will make such a line in space-time, and a line representing the history of its motion in space-time. Such lines are called world lines. So we talk about a world line of an object. So this is a world line of an object at rest relative to the yellow observer. And they are a really, really central notion in relativity. They are pretty important because basically any object, when you chart where it was in space relative to some observer and how this position was changing in time, you will get a line, some sort of a line. So this is object at rest. This was pretty simple. What about an object that's moving at a constant speed? So let's say we have an object that starts at 0 and it's moving at a constant speed. So after some time passes, it will cover some distance, and after some time passes, it will cover the same distance again and again and again. So basically, this will look something like this. It will still make a straight line in spacetime. Only this time, the line will be at an angle to the time axis of the observer, and this angle will be the greater this angle, the greater the speed of this object, right? Because okay, I heard a weird sound. Anyway, I hope you guys can still hear me. Oh yeah, I know, my headphones turned off. Okay, never mind. Okay, so yeah, the greater this angle, the greater is the speed of the object, because, well, the distance between the time axis and this line represents the distance covered by the object, right? So if in the same amount of time it covers a greater distance, then it moves at a greater speed. And actually, if we, let me quickly draw this. So if we look at some point here, and at some point here, so we have the time that has passed to the yellow observer, the time that has passed is here, and the distance that was covered was here. So then speed is just delta x divided over delta t, right? And this happens to be exactly the tangent of this angle, right? Because delta x is also here, and tangent is opposite divided by adjacent. So tangent of this angle is the speed. Actually, what I should say, this is speed divided by some constant, because it depends on the scale, right? If I stretch the x-axis, the angle this line makes with the time axis will change, but the speed actually won't. The actual speed won't change. It's just that I decided to use different units on the x-axis. So the choice of units will affect the scale, basically, of how big of a unit of a distance is on the x-axis, how big a unit of time is on the t-axis. So there should be some constant here, which will have dimension of speed. So basically it can be in, I don't know, meters per second or something, which defines what is the scale. And then, okay, maybe I wrote it in the wrong place. So V over A is tangent of this angle alpha. That's what I meant to say, because V is of course delta X over delta T. So this A is basically a constant expressing what scale we chose for the distance units and for time units. This will be somewhat important later, but maybe not that important. This is just
When you
something.
talk about the,
Hmm?
like, you said meters per second?
For example, meters per second. I meant that this constant A is basically some speed, so it can be meters per second, it can be miles per hour, it can be whatever, really.
Okay.
Doesn't really matter. It's just some constant. It's just some constant that controls the scale. Yeah, I hope that wasn't too confusing, but later, I mean, just to be
It's very
precise.
important, yeah. So, yeah, thank you.
Yeah, it will be important at some point. It's not that important right now, but it will be important at some point. Okay, let me erase this for now and continue. Okay, so we have an object at rest, we have a moving object, so an object moving uniformly looks like this. And if the object moves non-uniformly, then it can look something like this, for example. So the angle between vertical and the basically tangent to the world line changes, in which case this means that the speed was changing, right? So first the object was moving to the left, then it stopped, then it started moving to the right, then it stopped again and started moving to the left again. So this one moved non-uniformly, it was accelerating, and if there is acceleration, then world line will become curved. But for now, we will just focus about uniformly moving objects, because this will be quite enough to see a lot, really. Okay, so now let's introduce some actual units, especially for time. So let's imagine that this yellow observer had a clock with them, and the clock was ticking. So the clock was at 0 here, and it started ticking, and it made some ticks. So for example, it could look like this, right? So we have 1 unit of time, 2 units, those could be seconds, those could be hours, those could be years, doesn't matter. Some unit of time, then a second unit of time, third unit of time. A clock is just something that makes ticks at regular intervals. So this observer was holding a clock, and we now have those ticks. And basically, for every such a tick, there is a whole set of events that to this observer are simultaneous with this tick. And which events are simultaneous were those that are on the line parallel to the x-axis. So for example, we could draw it like this. Those lines will represent the events that are simultaneous with every tick. And they are called, not surprisingly, lines of simultaneity. Yeah. So, for example, now
Can I ask a question?
Sure.
Okay, so far there's nothing put on the table that would be different than what you do with Newtonian mechanics, right? So at this point,
yes,
there's nothing.
Yeah, so we'll get to that at some point, but I want to kind of introduce this gently. So for now, I'm not even going. You will see. So let's not get ahead of ourselves.
Just make sure I'm not missing anything.
Yeah. So there is like nothing weird going on yet. I'm just kind of explaining how spacetime diagrams work and trying to give you a feel of it. Okay. So now if the red object is also a clock, for example, and it's ticking, and if it got synchronized with the observer's clock, which can be done using any number of methods, it could also have its own ticks. So, well, basically if they are synchronized, then it will tick 1 second here where this clock ticked 1 second, 2 seconds, etc. Right? So it will look something like that. All right, so now we come to the big question. So we have this moving object, and let's assume that when it was passing by the yellow observer, so right at this time equals 0, they synchronize their clocks. And this is very trivial to do, because basically when they are passing each other, they are at the same point in space. So basically they can just quickly take a glance at their own clocks and see, okay, that's the difference, then reduce this difference to 0, and okay, we have clocks were synchronized at this point. So now the big question, so green clock shows 0 here as well. And now the big question is, where does the green clock show 1? So you might be wondering, why is it even a big question? I mean, isn't it obvious, right? We just said that those are the lines of simultaneity, right? So well, it would be obvious that since 1 unit of time passed for this clock here, so 1 unit of time should have passed for this clock here as well. Okay, so let's mark this. And this is a valid answer, actually. I mean, it's one possibility. What is not obvious, maybe, is that this is not the only possibility. But let's explore it. This possibility for a moment. This is a very reasonable possibility. Actually, this is how humans perceived the world for hundreds of years, really. This is basically the notion of absolute time, right? So we have some time that is passing, and we have those lines of simultaneity, and they are the same for each observer. So if 1 unit of time passed for this observer, then also 1 unit of time had to pass for this observer and for any other observer. So basically, the green clock would tick 1 at this point. Let me just consult my notes to see if I'm not missing anything that I wanted to say. Okay. Okay, right. So this is an option. So let's ask one more question before we move on to consider other options. Namely, what does this space-time look like from the perspective of the green observer? So now we are looking at it from the perspective of the yellow observer, right? When the axis of time is vertical and the axis of and the space axis is horizontal. And now, basically, in the green object's reference frame, in the green observer's reference frame, it should be vertical, right? So we have to transform this space-time somehow so that this green line becomes vertical. And we can do that. And one more thing that we have to do, we have to preserve those lines of simultaneity, right? Because basically we just claimed that, okay, when 1 second passes, then 1 second passes, so it should be the same everywhere, so this shouldn't change. So what we can do, and this is why I'm doing this presentation in Inkscape and not in some other software, what we can do is we can do such a transformation. And voila. Now we look at the spacetime from the perspective of the green observer. So now the green observer is vertical and it's at rest relative to itself, and the yellow observer and the red observer seem to be moving relative to the green observer, and they are moving to the left this time. And as time passes, their x coordinates, now this x-axis becomes the green observer's space axis, their x coordinates decrease, right? So after 1 second, this one is here and this one is here, etc., etc. They are moving to the left. Okay, so this is how we look at spacetime from the perspective of another observer. But this is not the only way. I mean, let's go back. Maybe let me just hit undo. Okay, but now that we drew okay, yeah, one more thing that I wanted to say. So what I just did here, this skewing of this transformation, the way this transformation looks like is, yep. So those are the equation of this transformation. Basically, from x coordinate, we subtract the velocity multiplied by time, the relative velocity of those two observers, and time remains the same. So this is what's called the Galilean transformation. So thank you, Dr. Clive Wells, who is on my chat on my live stream. Yeah, that's exactly the Galilean transformation. And that's basically that's basically how people looked at this stuff for a long time. Yeah, let's go back.
That would be Newtonian mechanics, right?
Yeah, that's basically Newtonian mechanics. That's mechanics like pre-Einstein, right? So we just take
there's the same thing, right? Sorry.
What do you mean?
Like
No.
only one is a more profound description, right? Einstein.
Okay, well, I think you are kind of getting ahead to gravity, but we're not talking about gravity yet. So this is like kind of the structure of just the basic structure of space-time. So we're not at this point yet. So right now, yeah, this was just the Galilean transformation. but there is kind of an obvious other option here. So if we look at this and we want to look at the spacetime, let me also hide this. If you want to look at the spacetime from the perspective of the moving observer, we just said that we kind of have to make this line vertical, right? So isn't there kind of an obvious option that's this? Let's just rotate this, right? I mean, this is also a way to make this line vertical, and this is also a perfectly valid possible answer. And actually, this already starts showing some weird things. Okay, so now let me just remove this this grid for now. Let's forget about this, and let's add now. Where do I have this? Let's add this. Okay, so I didn't really make this vertical. Okay, so now this is vertical. Okay, so now we have a different frame for the green observer. So now the time axis is here, but the space axis is also different. The space axis is still perpendicular to the time axis, but since the time axis is pointing in a different direction, the space axis is also in a different direction, right? And what also happens, basically, yeah, I showed this a bit too early because I wanted to kind of build up to this moment, like where should the ticks be on the clock, but I mean, no observer should be better than the other, right? So if we had this observer, okay, something broke, sorry. Okay, I moved the center of rotation for some reason. Okay, so if we had the yellow observer like this, and the ticks were just here 1, 2, 3, 4, 5. If we look from the perspective of the green observer, we should put them in exactly the same place, right? There is no reason to put them elsewhere. So this should look like this. And basically those ticks, this 1 and 1, should just lie on a... Where do I have this? Sorry for those... Okay, here. Should lie on this circle. This is basically just a unit circle around the origin, so all the points that are at distance 1 from the center. So this is one possibility. Look at this from this perspective. Okay, but now what happens? Now let's look at how time works now, because if we look at this green observer and 1 second passed here, if we look at the line of simultaneity, this line of simultaneity crosses the yellow observer at a point that's not at 1 second. Let's assume those are seconds, right? So here 1 second passed, but here it is at a point greater than 1 second. So more than 1 second passed for the yellow observer at the same time. But also if we return to the if we return the yellow grid to existence, same is true in reverse. So when 1 second passed for the yellow observer, if they look at what events are simultaneous with their 1 second, they will also see that more than 1 second passed for the green observer, right? So essentially each of them sees the other one as having faster clocks. Because for me 1 second passed, for them more than 1 second passed, so it seems like they have a faster clock than me, but this is true for both of them. Both of them see the other one as having the faster clock, which is one of the counterintuitive things about relativity, but also, okay, because I'm getting a bit ahead of myself. Now, if you heard a bit about relativity, you might have noticed that something is a bit off here, because in relativity, it is said that moving observers have slower clocks. And I just said here that the other observers' clocks are faster. And that's true. That's because this is not relativity yet. This is just the second option that we can use to transform the coordinates. But there is also a third one that will actually be relativity, but we'll get to it later. For now, let's look a bit more at this, because some things can be already seen here. And actually, intuition that we get from this example will be very helpful when looking at actual relativity. This, I mean, at least for me, it was very eye-opening to see the analogies between how just rotating a coordinate system works and how relativity works, because there are really many analogies there. Okay, but yeah, as we saw, we already have time dilation, right? Because one observer sees 1 second passing, and the other and it sees that the other observer more than 1 second has passed. So there is time dilation, only in the wrong direction, because moving observers have faster clocks. And also we have something happening to the distances. So if we look, for example, at the distance between the object at rest and the yellow observer, right? So we can imagine that they hold two ends of some kind of a rod, for example, or two ends of a piece of string. So the distance for them, the length of the piece of string, is basically this distance here between those two lines, right? But the distance between them for the green observer is, maybe let me draw this. So for those two observers, this is the distance, right? So here and here. And for the green observer, the distance is here. And we can see that the distance is greater for the green observer than for the yellow observer and red observer, if this is an observer, right? So the green observer sees the piece of string or the rod that the yellow observer and the red object are holding. It sees as if it grew in length. So we have the exact opposite of Lorentz contraction. Like length doesn't contract, it stretches for moving observers. But something happens to length. So we have those two effects. We have time dilation and we have length, stretching. And also we have something called relativity of simultaneity, but this was kind of visible from the start because the lines of simultaneity for the yellow observer are here. Those are those yellow lines, and for the green observer those are those green lines, and they are different. They are not parallel. So events that are simultaneous to the green observer, for example. So let's say I don't know, this event and this event. So to the green observer, those are simultaneous. They both happened at 2 seconds. But for the yellow observer, one of them happened at 1 second and one of them happened at 2 seconds. So they are not simultaneous to the yellow observer. So we have relativity of simultaneity here. Okay. Let me take a look at my notes. If there is something. Okay, I know what I wanted to say. Okay, so let's also write equations for this transformation that we just did here. Yep. So the transformation now looks like this. It's a bit more complex, and if you know relativity, you should already start seeing some similarities, because this kinda sorta almost looks like the transformation from relativity, but not quite. Some signs are different. And there is this A instead of C, so I didn't want to call it C with this transformation because this has nothing to do with the speed of light. It's like before, it's just some constant that relates the space units to the time units. It wasn't that important at the start, but right now it's very important because this transformation mixes space and time. So if we show this circle again, right, those are all the points that are one unit away from the center. So this 1 unit of time here is in some sense equivalent to 1 unit to the unit of space that is here. But what unit of space is it? Like what? If this is a second, what is this? Is it a meter? Is it a kilometer? Is it a mile? Is it a light year? What is it? We don't know. So that's what this constant is about. There is some constant that will relate the space units to time units, but we don't quite know what it is at this point. And yeah, that's what this transformation looks like. It looks pretty complex, but that's mostly complex because we decided to use speed, velocity, as the quantity that defines the relative motion between the observers. Because if space-time was actually rotating like that, a much more intuitive quantity would be simply the angle of rotation, right? And this angle of rotation is related to the velocity. It's related in exactly the way that we already outlined. So this is related this way. Okay, you don't see it that well probably.
Can you reverse the red and the green?
Red and the green.
Can you like flip them, or
what do you mean?
there's an object at rest and You know, the green is the observer, right? But can you flip that? Like the red would become the green, and then the green would become the red, right?
So you mean like
That's all.
rotate this whole scene or just flip the colors?
The reference frames.
So like, I mean, I can just take all of this. Okay, maybe let's hide. Sorry for a moment. There is a bit too much here, so I'm getting a bit lost. Okay, oops. Sorry about that. Yeah. So I wanted to do this. Okay, and now I can select everything. And now I could rotate this like this. Did you mean this?
Yeah. But I mean, the red would be the origin, though. That's what I meant.
Oh, the red. I mean, yeah, we could, but
Or it
I
doesn't
mean,
have that. It does not have that.
sorry?
So is it possible or is it not possible? Sorry.
It would kind of be possible. I mean, we could rotate relative to a different point, but kind of it's easier to see some things if the two axes that are important are intersecting at the center. So we would have to then basically extend this red to down, extend this green down as well, and then rotate about the point of intersection between them for this to make sense. I mean, I guess I could rotate around this point as well. It's nothing like it's not that important, but I mean it wouldn't really illustrate what I want to illustrate that well.
You're right. I don't want to interject, right? But that's an interesting image. But yeah, it's nothing. Thank you for answering that.
Yeah, no worries. Okay, let's just go back here, or maybe I'll just do this. Okay. All right. Let's. Okay. Yep. Okay. So what I was getting at was if we introduce this angle alpha as which tangent is just the velocity divided by this constant a. So basically, then it will simply be this angle here, angle alpha. Then if we use this angle alpha to express this transformation, it will turn out that it's quite a bit simpler. Well, depending on who you ask. You could write it like this. And if you know what rotations look like when expressed in coordinate systems, then basically this is a very typical rotation transformation. Like you have coordinate multiplied by the cosine of angle, and you add the other coordinate multiplied by the sine of an angle. There is this a in places here, but that's just because we use different units for distance and time, and there is need for some constant that will relate them to each other. But other than that, it's just a regular rotation. If we multiplied this this second equation by a, we would have 80 prime equals 80 cosine alpha plus x sine alpha, and then the analogy would be complete. We could just use 80 instead of t as the quantity, for example, and then we would have units of distance on both the time axis and the space axis, and we could use the same units for both. So that's one option. Or we could just write this a everywhere here. It doesn't matter that much. But yeah, I'm only showing those equations because there will be a nice analogy later. But yeah, let's not get ahead of ourselves. So let me reset some of this, or maybe let me consult my notes if that's all that I wanted to say on this topic. Okay, yeah, let me reset this. So what do I have to hide? I have to hide this. Let's hide this for now as well. And this, let's just, oops. Sorry about that. Let's just rotate back so that it's, okay. I will actually align it using the other frame. Okay, and something broke. Okay, this should be here. Okay, those are aligned, and why? Where is the center of rotation here? Okay, let me return it to where it should be. Okay, perfect. All right. So we're back at this. Okay, so we discussed two options for where the first tick of the clock, of the green clock, could be on this line. So one option was here. So that was the Galilean option, and there was another option somewhere here. So that was the rotation option. And the third option, so this is exactly on the line of simultaneity, the Galilean one, and the, let's call it Euclidean one, is below this line of simultaneity. So it shouldn't surprise you that the third option is that the first tick is above this line of simultaneity. So that is somewhere here. Maybe not exactly, but basically that's the idea. So now those three kinds of, I showed you two types of transformations, right? So one was just simply skewing the image so that the green line becomes vertical. One was rotating the image so that the green line becomes vertical. And there is third kind of transformation, which, no surprise, is the Lorentz transformation. That does something a bit different to this whole diagram, and we'll see what exactly in a moment. But one thing I want to say, actually, those are the only three kinds of transformations that satisfy some assumptions. And those assumptions are basically, first, that spacetime is homogeneous and isotropic. So what that means is that there aren't any special points or directions in spacetime. So basically, it's not like there is a center of the universe here and it's special and then everything revolves around it. Basically, every point in spacetime is equally as good as for the origin of a coordinate system. And every direction is equally as good for basically being some reference direction. So that's the first assumption. Basically, it's the general assumption that's being made in physics, that we aren't in any like privileged position and there is no special point in space that serves as the center. And another assumption is basically the principle of relativity, which can have many forms. This is sometimes stated as laws of physics should be the same in every reference frame, but I don't really like this formulation because it's not quite clear what it means for laws of physics to be the same. I sometimes state it as basically laws of physics should have like the same form expressed using only values relative to the reference frame. So there are no like absolute values that are relative to some special reference frame that are inbuilt into the laws of physics, for example. Here, in this example of just transforming spacetime, it boils down to the fact that the transformation in both directions should be the same. So basically, rotation is the same whether we rotate it one way or another, right? It's the same transformation, only with like the opposite sign. The same is true for skewing. It's the same transformation. And the third kind of transformation, Lorentz transformation, is also the same. The form is exactly the same, only some signs change if you basically reverse the transformation. So that's how you can look at it. And now I will show you what it looks like when we do Lorentz transformation on this. And actually, in order to show you this, I wrote a small plugin, small extension to Inkscape that makes a Lorentz transformation. It was possible to do it in another way. Okay, now, you know what? Because now so much has moved that I no longer know if this is the same place. I don't know if those coordinates are correct, and I wouldn't want this to get broken, so I have to show status bar. Okay. And let's see here. 579 and 939. Okay, so it did move a bit. 579, 939. Okay. All right, let me go to close to 0. And yep, let's see what happens if I start transforming this. So if I move this way, some weird stuff happens. Okay, this is, I don't think this is working quite that well. Is it? Oh, I don't know. Okay, it's not too bad. Okay, yeah. So if I increase the transformation, you can see that kind of weird stuff happened to this, but yeah, at some point, like at 0.6 here, 602, 6, something like this is close to vertical. So this is basically what space-time will look like from the perspective of this observer. Yeah, under the Lorentz transformation. If we go the other way, then the transformation does something like this. So yeah, it's a bit crazy, but not too crazy. Okay, let's write something like 602 here, because I think that makes it almost vertical. Let's check. Okay, can I or can I not? No, I can't. I have to apply this first. And then I can check if this is... Okay, yeah, this is roughly what I wanted. So let's leave it at that. Yeah, and the circle is no longer relevant. So let's hide it. Okay, yeah, this is what happens if we use the Lorentz transformation. So again, lines of simultaneity got skewed a bit, only this time that it got skewed in a different way. So now if we look at what happens, we can see that now the time dilation is the other way around. So if we look at the line, this green line are the events that happened at 1 second according to the green observer's clock. And we can see that at 1 second for the green observer, for the yellow observer, less than 1 second has passed. So now the clocks of the moving observers are moving slower, which is exactly what we expect. Now, where exactly is this one? So yeah, we had this circle here still, so that was relevant for rotations. But it turns out that there is a shape that is relevant for Lorentz transformation. And this shape, I hope this will show. Yep, this shape is a hyperbola. So as you can see, both ones lie on the same hyperbola that's passing through those axes. So actually, if I can actually show this to you. So if I select all of this so that the hyperbola is also selected, and if I now start doing Lorentz transformations on this, maybe not 0.6. Okay, so if I start doing transformations, the hyperbola stays in place. So what we could say is it is invariant under Lorentz transformations. So that's one shape that stays invariant. We could draw more hyperbolas, not just the one passing through one. So we could draw more, and we will have hyperbolas corresponding to 1 second, to 2 seconds, to 3 seconds, to 4 seconds. And basically, if the clocks show 0 here, then those hyperbolas are where the clocks will be showing 1, 2, 3, 4, 5 for different observers. Okay, one thing that we might notice is that here the transformation doesn't mix time and space. What I mean by that is with rotation, if we basically when this was moving points around circles, not hyperbolas, if we rotated the coordinate system far enough, we could rotate it by 90 degrees, and then time and space would switch places for the two observers, right? So there could have been an observer that's moving relative to the original observer at such a speed, actually at infinite speed, that had time in the direction in which the original observer had space, and vice versa. Here, as you can see, this is impossible, because no matter how much we transform this, those time axes will always point upwards. Well, maybe a bit more to the left, a bit more to the right, but always upwards. So it's not possible to transform it so much that time and space change places. So we can so for space, we need a separate set of hyperbolas like this. And they would also be unchanged by the transformation. So those are kind of analogous to circles in rotations, only like in Lorentz transformations. And there is actually one more thing that's unchanged. So all those hyperbolas are unchanged, but the closer you get to the origin, those hyperbolas get closer and closer to actually just straight lines at 45 degrees angles. So this will also be unchanged by Lorentz transformation. And now this should be interesting because...
Can I interject?
Yeah, sure.
Yeah, the same thing is going on, but the other way around, right? So right now we're just seeing, you're showing us a half, but there's another half going on.
Yeah. I mean, this could also be extended to the left and to the bottom, right? So
Yeah, well, I mean like antipodal, like there's, I don't even know if that makes sense, but like what you're showing us is only half the equation, right? The same thing is going on in the opposite direction.
yeah, if I understand you correctly, yeah. Yeah, so yeah, like in this direction, for example, yeah. So I just drew this single line here, but actually this will be true for any line at 45 degrees in this diagram. So those lines will remain unchanged. And this should be interesting because, okay, straight lines at angles to vertical correspond to objects moving at some speed, right? So now, if there was an object that was moving at such a speed that its world line would be exactly this line 45 degrees to vertical, then no matter how we transform the coordinate system, this line will be unchanged. So it will always be at 45 degrees. So such an object would be moving at the same speed in all reference frames. And that should sound a bit familiar because this is exactly what according to relativity happens to light, right? I mean, there is a lot of that's one of the postulates really of relativity, that the speed of light is the same in all reference frames. So this is basically why. If the Lorentz transformations preserve this direction at 45 degrees, and this happens to be in relativity, this happens to be corresponding to light speed. So light speed is the same in all reference frames. Yeah. Okay, sorry, just consult my notes. Okay, yep. So what I wanted to show as well, let's take a look at time dilation and what happens to length. So with time dilation, let me hide those hyperbolas because they are. Oops, sorry, because they are a bit much. So let me hide those. Okay, so we were already looking at time dilation, so I already noted that for 1 second for the green observer, less than 1 second passes for the yellow observer. And again, the converse is also true. The lines of simultaneity for the yellow observer got skewed this way, so that basically when 1 second passes for the yellow observer, if we follow this line of simultaneity, it again intersects the green line below 1 second. So again, we have this kind of symmetry between the observers. So it's not like one observer is special, the other is different. It's exactly symmetrical. And regarding the length, now it's a bit harder to see, but the length, again, the length, for example, between the red and yellow in the yellow frame is this, right? So it's this length, and the length in the green frame is, for example, this here. So we could say, okay, this is shorter than that and call it a day. But actually it's a bit more complex because this transformation doesn't really preserve distances like Euclidean distances. So just because this looks like a greater distance doesn't mean that it is a greater distance. Like, for example, this distance between 2 and 3 here on the screen looks greater than this distance between 2 and 3 here, but from the perspective of this spacetime, those are the same distances. So what we should really do is draw a hyperbola here that will go, okay, so let's extend this a bit, okay. And now we would have to draw a hyperbola through, let me think. Yeah, so between here and here is this length, and if we want to see what length this corresponds to, we would have to draw a hyperbola through this, and it would go somewhere like this. So this length actually corresponds to this length. and the measurement that the green observer would make would be the length up to here, so this length. So now, so this object is indeed contracted when it's moving. So the length that the green observer measures is less than the length that the yellow observer measures, which means objects in motion are shorter, which means we have Lorentz contraction. And of course, we have relativity of simultaneity like we had before, only it works like the other way around now. Okay. Yeah, so let's again look at the equations. So if you ever saw a textbook on relativity, you probably saw those equations. So those are the equations for the Lorentz transformation. And as you can see, those are pretty similar to those for rotation. Let me pull those up as well. Okay, so those were for rotation. And those are for Lorentz transformation. So you can see that those are indeed very similar, only instead of plus in the denominator we have minus, and we have minus here as well instead of plus here. So those are the differences. And I wrote C here instead of A here, because this time C is actually related to the speed of light. In relativity, that's exactly the speed of light. But again, let's not get ahead of ourselves. We'll get to there, because this doesn't have to be as the speed of light. I mean, the transformations, there is a whole family of transformations that would be, that basically would satisfy those conditions of homogeneous isotropic spacetime and principle of relativity with with basically an arbitrary speed here. So how do we know what this that actually this transformation is what corresponds to nature, and how do we know that this C here is actually the speed of light? In a moment, but first, before we get to that, I wanted to show you. So in the case of rotation, there was an option to basically introduce some kind of an angle that we could rotate. Basically, we could express the rotation in terms of an angle instead of in terms of this velocity. So is this also an option here? Well, yes and no. No in that not with an angle, but yes, there is an option. We can introduce a quantity that is called rapidity. So this is the Greek letter eta. I think it's pretty commonly used for rapidity. I'm not quite sure, but that's one of the notations I know for rapidity. Yeah, so this is kind of like an angle, but not quite, because this tangent is not the regular tangent, it's the hyperbolic tangent. So as you can see, hyperbolas are popping up everywhere in relativity. So yeah, if we do this substitution, then this equation can be written the following way. And again, there is some similarity to rotations. I mean, if we just replace those hyperbolic functions with trigonometric functions, and we replaced the minus here by plus, we would just get a rotation. But as it is here, it's not a rotation, it's a different transformation, and it uses hyperbolic functions. Why am I telling you that? Because this has some nice implications. So let me hide all of this for now. So let's go back. Wait, this is also not needed. This is not needed. Let's keep this for now. Select this. Let me return this to the original. And you will notice that I also use the name rapidity here, because that's exactly what it is in. Okay, let's just put it at 602 like it was before. Okay, apply, close. Okay, so for example, let's go back to this Euclidean example again. So let's assume we can just rotate the frame. And let's assume that this moving object is, for example, I don't know, a bus or a train or something like that. And that this observer, this green observer, is throwing a ball, for example, ahead of them. So if they throw it at exactly the moment 0, Oh, sorry. How do I? Okay. If they throw it exactly at moment 0 and they throw it at some constant speed, then the ball will fly, like, for example, like this. So the speed relative. Sorry?
So I play basketball, right? I like to play basketball, you know,
Okay.
my local park.
I
So
see.
when I'm throwing a ball, it's doing that.
I mean,
How does that
if
count for that, dude? Like,
it-
in order for me to in order for me to be Shaquille O'Neal, I would have to you know, account for this.
yeah, in practice, it's not really important because basically speed of light is huge, and then in practice, this would only get important if you were throwing or hitting the ball at close to the speed of light. As long as the speeds are small, it's not really important. Like, okay, I'll show you something later, but for now, okay, or maybe I can just show you right now. I mean, if you take a hyperbola and you zoom in really close on it, it will almost look like a straight line. A circle as well, to be honest. So basically, whichever of those three types of transformations it is actually in reality, as long as this constant velocity that appears in the equations is huge, this would all look to us as if it was basically the Galilean transformation, because it would basically look as if we're transforming everything along a straight line, not exactly along a hyperbola or along a circle, even if it was truly like this. Anyway, what I was getting at, if something is let's say thrown at a constant speed, and it's moving at a constant speed relative to this green object, so we can figure out its speed, we can see what distance it covers and at what time, we can divide this by this and we can get its speed. So now what is its speed relative to the yellow observer? Well, let's say the green object moves at v relative to the yellow observer, and the red object, this red object is thrown with a speed of u relative to the green object. So now what is the speed of this red object relative to the yellow observer? Now, if we were in the Galilean world, we would just add those two velocities together, right? Because then basically everything would be along the same line, and we could just add those two, and we would have the results. But now, because in this case we are rotating the reference frame, basically this speed, this thing divided by this thing, is not the same as this divided by this plus this divided by this, for example. So because velocity is basically a tangent of some angle, what we really add here is the angles and not the tangents. So like if this is angle alpha, this is angle beta, we have tangent alpha plus beta. There is a trigonometric identity for this, and this is actually tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. So if we actually substituted, if we did this, v over a equals tangent alpha and u over a equals tangent beta, then this, in quotes, v plus u, so this proper addition, not direct simple addition of velocities, but the actual velocity of the red object relative to the yellow object, will be based on this tangent of a sum of angles. So it will be something like v plus u, but divided by 1 minus v times u divided by a squared. Something like this. So this is how velocities would add if the world was Euclidean, like if space-time was Euclidean, if transformations between different reference frames were just rotations. That's how this would work. But transformations between frames are not rotations, they are more complex. So if we now go back with this, let me rotate this back. Okay, let's hide the green frame and let's do the Lorentz transformation again by 0.602. Okay, perfect. Okay, so now if the green observer throws something here at some speed u, and it was moving at some speed v relative to the yellow observer, how do we add those speeds? And actually, it's very similar in that in the rotation case, we could add the angles. Here we can also add something, the thing that is analogous to an angle, so rapidity. So if this corresponds to rapidity, like if u divided by c is hyperbolic tangent of some rapidity 1, and v divided by c is the hyperbolic tangent of some rapidity 2, then this u plus v, this velocity of this red object relative to the yellow observer, will be simply the hyperbolic tangent, well, c times the hyperbolic tangent of one rapidity plus the other rapidity. And there is also an equation for the hyperbolic tangent of a sum of well, rapidities in this case, and we can write it as hyperbolic tangent of the first plus hyperbolic tangent of the second divided by, and it is very similar, only it's the plus sign here instead of the minus sign, and we can multiply those tangents. So if we write this in terms of velocities, what we get is u plus v divided by 1 plus uv divided by c squared, which is exactly the formula that you get in special relativity. Okay, so that's how you transform speeds. So the important takeaway here is that if the spacetime was Galilean, then the speeds would just simply add. If it was Euclidean, if transformations were just rotations, then the speeds, the combined speed would be more than a simple sum than the speeds. And if it's Lorentzian, like here, then the combined speed is always less than the sum of the speeds. So if those are both positive, right, then we have the sum of the speeds here. But here we divide by something greater than 1, so it's smaller than the simple sum of the speeds. So this actually provide a missing factor of c in intermediate. Yep, exactly. Yep, there should be c here. Yep, thank you. This was a message in the chat on my stream. Okay, yeah. So this here actually provides an opportunity for experimental verification which of those transformations best corresponds to reality, because we can measure how speeds combine only if the speeds involved are huge, if this c constant, which we know that is the speed of light actually, but let's say we don't know. So there is just some constant c, and if this constant c is huge, then we also need huge speeds to see if this addition of speeds is the same or different than in the Galilean case. So, but actually there is a way of doing that, and it actually has been done in 1850s. Before anyone even thought of relativity, like a few decades before. It was done by a French physicist, Fizeau, who came up with a brilliant way of measuring the speed of light. I won't go into the details how he did that, but basically I believe he was the first person to just directly measure the speed of light in a laboratory. And he didn't just measure the speed of light in the air, he started doing measurements in water and in moving water as well. And what he found was that the speed of light in moving water is less than sum of the speed of light in standing water and the speed of water, which back then got interpreted as argument for the ether, actually, for some particular theory of the ether. But if we don't want the ether, and we, in light of those possible transformations of spacetime, we can see that it could be also interpreted as evidence for this Lorentzian spacetime. And actually, based on how much exactly this sum of the speeds is smaller than the simple sum of the speeds, it is possible to figure out what is this constant c. And as it turns out, if you do the math, it's surprise, surprise, it's the speed of light. So yeah, so basically this is one of the pieces of evidence. I especially like this one, and I mean, this is, again, after my professor at the university, so I believe he especially liked this one because this is an experiment that was made before anyone even thought of relativity. So, like, it couldn't have been manipulated or anything to provide evidence for relativity, and yet still it is very good evidence for relativity. You can compute the constant in those transformation equations, and you come up with almost exactly the speed of light, like within measurement uncertainty. And obviously currently, like in the modern world, we have a lot more evidence for special relativity, for the fact that the transformations between reference frames are actually those kind of weird hyperbolic rotations, so to speak. But yeah, I mean, I hope that those analogies, like between rotations and Lorentz transformations, I mean, for me, those analogies were like the aha moment. Like it suddenly clicked for me. Special relativity became intuitive. In order to figure out what happens according to special relativity, I just had to rotate the picture, but not quite rotate, but stretch it in one direction and then shrink it in the other direction, like what this Lorentz transformation does. And once you get this intuition how to transform stuff using the Lorentz transformation, and you can do this by just drawing a few like hyperbola and basically keeping those 45 degree angle lines always in the middle of the angle between the axes. Like here, the yellow t-axis and the yellow x-axis don't make a 90 degree angle, but if we, where is the light ray? Sorry, it's not this, here. Yeah, if we draw the light ray, it's still in the exact middle, in the half of the angle between those two axes. So if you keep that in mind, you can kind of figure out what goes where, and then this all becomes fairly intuitive. So I mean that if there's takeaway from today, I hope that this made it a bit more intuitive for you. And yeah, I already exceeded 1 hour. I was already speaking for 1 hour and 13 minutes, so I think that's a good place to stop. And that's actually all I had prepared. I thought that I was wondering if that was going to fit within 1 hour or not, but yeah, I had a good feeling that it wouldn't. So thank you for your attention, and I guess I don't know what is planned next, some kind of after show or something, but yeah, thank you.
Thank you for the presentation.
Yeah, thank you very much. That was really great. I really liked the way that you went through and established geometrically how things work. Maybe this is a topic more for the next time, but something that I still don't quite understand is this idea of the speed of light as somehow being really like a measurement of the speed of causality. Is that something that you address specifically, or is that something you can speak to? I know that's kind of a big topic, but
kind of. I mean, okay. Let's put it this way. So I actually can kind of address this using what I already said today. Let me just turn a few things off because there is maybe a bit too much in this picture. Okay. If I do this, but turn this, no, this, let's leave, let's turn this off. Okay. So, so as I mentioned, there are those hyperbolas that are preserved by the Lorentz transformation, right? And they don't mix space and time. So no matter how you transform, no matter how big of a boost. Okay, so Lorentz transformations are often referred to as boosts. So if you transform using a Lorentz transformation, it is said that you boost the reference frame. So no matter how much you boost a reference frame, you will never leave those the area of those hyperbolas. So if there are two events that are causally linked, right? So that will mean that one happened after the other in some reference frame, possibly in the same point. So let's say in some reference frame, those are the two events that are somehow causally linked, right? So the thing is, with Lorentz transformation, as you can see, because no matter how you boost this, those two events will have to stay on those two hyperbolas. So it is possible that in some reference frame they will get boosted like to here and to here, right? But no matter what you do, if this is B and this is A, B will always come after A, right?
I see.
So,
Okay.
but that is only true if you have two events that are connected by a line that goes slower than the speed of light, right? So as long as you have two events, if this is the first event, okay, as long as you are within this area delimited by those light rays, Like for example, okay, and this is event A. Okay, maybe let me just draw it from the start. Okay, so if this is event A, right? So as long as event B is somewhere here, like within this, you can always boost it so that it's in the same place after event A, but no matter how you boost it, it will always be after event A in all reference frames. But if there is an event B prime here, and we have those spatial hyperbolas, let me here, okay. So now boosts will move this event B prime along this hyperbola, and it is possible to boost to find a reference frame such that this event B will go from here to here, which means that those two events cannot be causally linked, because in one reference frame B prime was after A, but after we changed the reference frame, this got moved to before A. So there is no like set sequence of events, right, for those two. And where that happens, the limit between those events that are always in the same sequence and the events that are not necessarily always in the same sequence is the speed of light. It's this line, right? So events on one of those on one side of this line will always stay after A, and events on the other side will be sometimes after A, sometimes before A, depending on the reference frame. So that's kind of where this notion of speed of causality and this limit of the speed of light comes from.
Okay. Cool. And so if there was a non-constant speed of light,
Go on.
yeah, if there was a chill AI. If there was a non-constant speed of light, what would be the implications for causality and the laws of physics?
Kind of hard to say, really, because that's a bit beyond relativity. I mean, I guess the main question would be, what does it mean for the speed of light to not be constant? Because in light of this geometry, the speed of light really just defines how units of space and units of time are related, right? And currently, even we define units of space meter is defined by the second and the speed of light. So the speed of light is like set to an exact value. So one could argue that a different speed of light would just manifest as different measurements of distances, in which case we might not really be able to notice, because if we measure using this, space-time with a different speed of light would look exactly like space-time with this speed of light, but like with different units of distance, for example. So there wouldn't really be any way to tell that there is a different speed of light. I mean, okay, there is like one way to tell, because there is this, at least one way, because there is this constant that is, what's it called? That's like a fine structure constant, something like that. It's a combination of the speed of light, of the charge of the electron, and of Planck's constant, I believe, something like this. And basically, this is a dimensionless number, so it doesn't depend on the choice of units. No matter what units you choose, this number stays the same. So if you change only the speed of light, but not the charge of the electron or the Planck's constant, you would get a different, this fine structure constant. And this would be a way of noticing that something is amiss, right? So if you do a measurement in some different place in the universe and you get a different fine structure constant, then that's the indication that something changed. But not necessarily.
If you one thing that would more one when you mean like over time that the speed of light would change, or locally the speed of light would change?
Yeah, that's also a good question.
Well, the Aether boys say that there's an ether wind that causes a differential in the speed of light and changes the preferred direction based on where you are on Pizza Planet.
Oh, that would violate an energy conservation very fast.
Okay.
Yeah, that would break quite a lot of things.
E
Wait,
equals
yeah.
MC squared would go out the window, and
Who's
you could
talking
get
about energy
free energy
conservation?
generation out of
Relax, buddy.
nothing.
Relax, buddy.
Well, that they do believe in free energy typically, so that's not a
Okay, yeah.
problem.
Yeah, Totoro, it sounded, yeah, just don't appeal to emotions in front of everybody. It's not good. It's not a good look.
All right. Well, that was a pointless comment. thanks so much, Science. I appreciate this presentation. This was super helpful.
Thank you.
Anyone else have any other questions? Or, I mean, we could go to open discussion and we can just keep chilling in the voice channel. So,
Let's go to discussion, I guess.
I see I have some
Yeah.
highlights in the chat. Let me. Okay.
Yeah. So it's all centered, you know, around the observer, right? Hello?
What do you mean?
Like, you know, the origin point is the observer, right? 0, 0.
I
Not
mean, 0,
necessarily.
0 is just some moment. Like the observer is.
No, but
the observer is really like this, more like this line, right? So basically, this, as time passes, the observer kind of moves in quotes, because it's not really motion, along this line. Like time passes, so the time coordinate changes, right? But space coordinate
yeah.
remains at 0.
So
Yeah.
yeah. So yeah, so every time you're making a measurement, it's time's going by, right?
Well, yeah. Yeah, I mean, everything is always described from the point of view of some observer. So, I mean, that's kind of how pretty much everything works. If you're doing a measurement, then if you measure anything in space-time, you need to if you measure a position, for example, of something, you need to somehow define the coordinates, and you need to put the 0 somewhere, so that kind of already ties it to some
Yeah.
reference frame. So
Yeah, I know, and like, you know, all the instruments are, you know, more or less, you know, put that into consideration, right? So I want to take the spotlight, right? So yeah, I'm gonna withdraw. So yeah, everybody, like, yeah, make your point. Sorry. Like dude, you're good, dude. Like you're the one like looking over us right now, right? So if somebody wants
all
to
right,
make
I have a question. I have a
positive
question.
claim.
Let me jump in. So one of the things that I was debating with Sid on yesterday was the extent to which special relativity was directly developed because of the Michelson-Morley experiment. And obviously then there's a lot of other conspiracy theory, tinfoil hat stuff that goes into that, which I won't mention, but
Yeah, because it was an
hold on, hold on.
initial.
Don't interrupt me. Don't interrupt me. Don't interrupt me. I'm just finishing my question. So, if you know, what is the evidence for the extent to which the Michelson-Morley experiments influenced Einstein? Because I know Einstein said different things on that topic.
Honestly, I'm not sure I can really answer that question, because I'm not that familiar with the historic side of things. I mean, obviously I know like general outlines, but I really have no idea how much Einstein was influenced by the Michelson-Morley or how much he wasn't. Like, I mean, from what I gather, I mean, that was like a big inspiration, but maybe not. Yeah, I mean, I really don't know.
Yeah, the history is important. But yeah, you
I mean, well,
you know a lot of
not for the physics itself. I mean, the history, of course, you can say it's important, because it's kind of important to remember how stuff came to be, and etc. But it's really not that important for the validity of the theory itself. Like, it came to be in some way, but then it turns
Yeah,
out
but
that it can be derived
yeah,
other ways from different assumptions, and you
it's
can
weird.
converge on the same result from multitude of different sides, and they all pretty much say the same thing, that this is kind of what works
Yeah,
best.
but that's low key weird. That's low key weird, dude. Because you know, dude, I lost my train of thought, dude. But yeah, that was a weird thought, bro. I don't agree with that. Like, history is very important, right? So, yeah.
Well,
So
not
who cares? Who cares
that's a little bit.
Who cares what
A little
3
bit
is if you don't know what 1, 2, and 1, 2 are, right? So
that's
you kept referencing
very
Galileo and and Newton, right? So these are important steps, right? But I feel like you jump to the conclusion and you neglect a lot. You neglect a lot of stuff. Sorry.
Okay, yeah, I mean, you have the right to your opinion, I guess, because I
If
don't
you're gonna
think
tell me history is not important, man, I think you have to go back. Go back in time, right?
important for
So it's
what,
your own
I would
device.
say. Because
Science, just a point of order. Just be aware.
Whatever.
AI likes to likes to ask pointless questions that
I
don't
see.
really lead anywhere. He usually doesn't make much sense anyway, even on the best of days. So just play with it or ignore it. One of those,
no, I mean,
probably.
okay, yeah, I mean, whether history is important, I guess it is a topic for a discussion, but I'm not sure if this is relevant to the topic at hand.
Yeah, not to the mathematics and the mechanics of the theory. It's
Exactly.
mostly
Well, yeah.
for science historians.
Now that you mention mathematics, right? So yeah, we know general relativity is like connected to differential geometry, right?
Yep.
So you got the half sphere, pseudo-Ramian, right? Is that his name?
Pseudo-Riemannian, yeah.
Yeah, pseudo.
So
Yeah. Well, you got all that right.
So basically, the pseudo part of pseudo-Riemannian, it basically refers to, okay, just a quick note, I guess. So Riemannian manifolds are basically, let's say, simply put, spaces that locally look like Euclidean space. Very like short summary. So pseudo-Riemannian are manifolds are spaces that locally look like this Minkowski space. So this basically this space that where transformations, where this main transformation is Lorentz transformation. That's the Minkowski space. And if you have like a more general space that only locally looks like this, that's the pseudo-Riemannian manifold.
I think Minkowski space is enough, right? So yeah, you guys got dunked on, right?
That kind of looks concave.
Somebody might have had a seizure because you said that.
I had a good laugh.
Can I ask a question?
Sure.
Yeah. So I wanted to ask, because these examples of transformations were done on objects that are moving with constant velocity. Because to transform to its reference frame, you have to make the line vertical, so it wouldn't be moving at all. But how do you transform it for an accelerating reference frame if the line isn't even straight?
Yeah, that's something that I would go into if I was continuing this this presentation, because kind of that's the next step towards general relativity, to look at what happens if the observer itself is accelerating. It becomes a bit more complicated, I guess. So
Hold on, we're always accelerating, aren't we? Right. 9.8.
Well, okay. I mean, that's not really relevant right now, but kind of. I mean, so what happens there is so you can always use the Lorentz transformation so that the observer is at rest at a given moment, right? So, for example, if there is an accelerating observer, their speed obviously changes with time. So at any given moment, they have a different speed, well, relative to some other inertial observer. So you can transform at any given moment you can transform spacetime at any given moment so that it's this observer is at rest. But you cannot really do the Lorentz transformation so that it's at rest all the time. But you can introduce coordinates such that the accelerating observer is at a constant space coordinate. Only that goes into a whole other territory of curvilinear coordinates, because then basically the diagram of spacetime is no longer it's no longer such a straightforward diagram where you have a plane and you just transform it into one way or another. You basically start diagramming stuff in coordinates that themselves are curvilinear, and that introduces all sorts of interesting effects to stuff what happens in these diagrams. So you can do that. You can consider accelerating observers, and it's pretty interesting. But yeah, I really didn't have time to go into that deeper. So that's something for part 2.
is very interesting.
Yeah, these equations, gamma and all the Lorentz factors, only special relativity basically just deals with inertial motion, so unaccelerated linear motion in the absence of gravitational fields. It's just the special case for the simplicity.
Kind of, although actually, I mean, okay, I would put it a different way, because that's actually something you often hear, that special relativity is only about unaccelerated motion, and accelerated motion already requires something more, but not quite. So special relativity really deals with the case where the space-time itself is flat. So flat in the sense of no curvature, like it's almost Euclidean, but not quite, because of this different way time works. But basically what you have is a space where you can have straight lines, and they can be parallel to each other, so you have something like a Euclidean space a bit. So that's where special relativity can work, and it doesn't really matter what the observers themselves are doing, as long as they are moving in a flat space-time. You can treat them with special relativity. You get some differential equations, of course, you get some weird stuff here and there, but that's still special relativity. General relativity really deals with the case where space-time itself might not be flat, might be curved, and it's not even possible to introduce like rectilinear coordinates, because there are no straight lines. You have some geodesics, but they can diverge, they can converge, this stuff can happen. So yeah, that's where general relativity really comes into the picture. But yeah, that's kind of getting ahead a bit. But for example, a phrase to Google if you want to check how accelerated observers can be treated in special relativity is Rindler coordinates. So this is like a very specific case of how you can introduce coordinates based on a uniformly accelerating observer.
Like the moment you said the word, I needed to Google. Like it was really you like mumbled through it, right? So can you repeat that, please?
Yeah, it's kind of hard to pronounce. Okay, I'll just write it in the chat. Let me just scroll down. Okay, wrote it in the live debate text.
Thank you.
So this might be a bigger question too, but where does the mass energy equivalence come from in this framework?
Yeah, that kind of that is a bit of a more advanced question. Like what you have to do to get to there, at least the way I know how to derive it, is you kind of start. Basically, you first need to figure out how to describe momentum and energy. And to do that, one way is to start considering collisions. So the simplest case of two identical objects colliding, there is some reference frame in which when they collide and let's say they collide and they stick together and they become one object, right? So the simplest case when those are identical is basically you can find a reference frame in which the product of this collision is at rest. And so because this was symmetrical, the objects themselves had to move at the same speed towards each other. So then you can write basically equations for before, for after. So okay, yeah, one thing that also comes into play, you define something called the for velocity. So it's kind of like a unit vector, unit or length c, let's say, that is tangent to the world line, that points in the direction of the world line, basically. So then there is a very easy way of figuring out if you go into the frame where the product of the collisions is at rest, then you can write those equations. It's pretty easy to figure out if you employ for velocities, because then okay, it's like a very short abstract of how this can be done. Basically, you write the four velocities, and the sum of them will have to be along the world line of the product, which then leads to some expression for So then you can kind of extract a factor from this result, because for velocity is supposed to be a unit vector, but the sum of the initial 4 velocities is not a unit vector. So you extract a factor, you identify it with the mass of the product, but then the mass turns out not to be the sum of the masses of the initial objects. And then you figure out that some expression there should be the momentum, some expression should be the energy, and then it all comes together into this big, like, that energy is basically mass times c squared times the Lorentz factor. But yeah, that was like a very, very condensed version of this, and it's probably not clear at all. It's a topic for a whole other like video / stream / presentation.
Yeah. Cool. Thank you.
Sure, you're welcome.
Yeah. How much you pay? How much did you pay Sea Lion for this presentation?
Wait, who? Me? How much did I pay for this presentation?
Yeah. It's your channel, right?
$10,000. And I'm gonna
Okay,
send
so
another $10,000 for more attendees. You have attendees in
so,
Poland, right?
okay, well, see that he retorted to lying, right? So yeah, the globe proponent is gonna do that most of the time.
He retorted the
you're welcome.
line. Is that what you just said?
You retorted to lying, right? So you came back to lying, right? So your defense mechanism is lying, right?
Oh,
Because
okay.
yeah.
Hey, I thought you were doing pretty good with actually raising relevant and productive questions. Why'd you have to go and ruin that for yourself?
Because you have to go ahead and talk, right? So yeah, I'm here for him. So I'm asking you,
Okay.
how much did you pay, right? So you said 10,000, right? So yeah, you're allowed to talk to him if you pay 10,000.
Oh, okay.
Yeah, go ahead.
One thing that's always fascinated me is that the speed of light itself can be derived from electromagnetism, just based on the scaling and strength of electromagnetism.
Yeah.
That derivation is really quite fun.
Yeah, that's true. That's pretty fun. I mean, yeah, that was one thing that was puzzling people, I guess, when they figured out the equations of electromagnetism, and they figured out, oh, hey, we can get the speed of the waves from there. But yeah, oops, one problem: speed of the waves relative to what? Because it comes out, but like relative to what? Yeah.
Yeah.
So then
I
there
would say
was
that's one of the. It's a fairly strong argument for the fact that the speed of light is constant, is because everybody measures electromagnetism at the same strength. All the electromagnetic interaction, all the chemistry works the same, irrespective of your relative motion. Because
pretty much.
if they changed, that would be kind of a clear signal that the speed of light or there must be some absolute reference frame, but that never happens. And it would not be a subtle change.
Because you're not Earth, right? So
it would not be a subtle
you're
change, because you
you're a
would get.
human on Earth. You are not Earth, right?
I have no idea what you're talking about. Yeah.
One argument I heard raised about this is that basically the color of gold is due to some relativistic effects happening to electrons in the gold atoms. So basically, the very fact that gold has its color, has the color that it has, is already evidence for relativity. I wouldn't be able to to basically tell you how exactly, because that's a bit beyond me. But apparently, yeah, there are some relativistic effects involved, and yeah, if speed of light wasn't constant, if relativity wasn't true, we could also expect to see changes in the color of gold in motion. Apparently.
Not just the color of gold, all of chemistry would start to vary based upon your speed, since chemistry is essentially all electrostatic forces and masses of objects. So you would start getting weird effects, like certain chemical reactions would start activating at different energy levels, energy boundaries. You would start getting things like water starting to boil at different temperatures, probably. That would get very strange.
Yeah.
There is a Roman cup, the like Kyrgyz cut or something like that. Depending upon whether light is reflecting off of it or passing through it, it changes colors from a gold color to a green color, and they say that is due to quantum effects. It's kind of interesting.
But actually, kind of, I mean, if you have a very thin layer of gold on something, then basically gold reflects yellow light, right? So it will look yellow when looked at in reflected light. But if it's a thin enough layer to transmit some light, then if you look through it, you will see green, because basically everything below yellow gets reflected, so everything above yellow gets transmitted through this layer. And if you combine the lights with wavelengths like above, well, frequencies above like yellow, let's say, so like green, blue, purple, right? So combined, you get like a greenish, bluish light. So that's kind of why you get those different colors when looking in reflected and in transmitted light.
Yeah, it's something to do with there's nano particles of like aluminum and some other metals in the glass, zinc and titanium. It's pretty cool.
Yeah, so the properties, I guess.
So when it comes to the difference,
the glass will be a copper glass or like a. You saying they're all mixed up, or are you talking about a copper glass, or are you talking about a gold glass? I'm confused.
gold
It's
glasses are
glass.
usually
It's opaque glass.
the only ones I use are
Right,
gold
gotcha.
glasses because that's how fucking classy I am. Anyway,
Right.
the difference
it's not wasting
between
money.
SR and GR then, and why it's called GR is that it deals with more general cases of space-time. Is that what you're saying, Steins?
Yeah, basically. So yeah, SR like works on a flat spacetime. So kind of like a plane is flat Euclidean geometry or just Euclidean three-dimensional space. It's also like flat geometry in this sense. And like if you go to like spherical geometry, hyperbolic geometry, or like anything in between, you get a bit weirder stuff. Like you need a bit different maths for that, like manifolds, differential geometry, stuff like this. So in the same vein, like special relativity deals with flat spacetime, and if there is some spacetime curvature, like that's the domain of general relativity. I mean, like the main like bit of general relativity is relating the curvature of spacetime to the distribution of stress energy, right? So kind of it already postulates from the start, yeah, you will have curved spacetime, but then like describing everything within this curved spacetime and how motion works, stuff like this, that's kind of also within its domain.
So when we talk about space-time, like to what extent did Einstein conceptualize it as an actual, I don't know if material is the right word, like material construct versus a mathematical representation of what can't be measured, maybe? I don't know if that question is well formed, but because Newton posited to some extent later on in his life that gravity needed to be explained by some medium that enabled action at a distance, right? And then Einstein kind of came in based on this geometric representation and sort of developed the idea of matter, curved space-time. But I just wonder, like, and maybe this is, we're getting more into history and stuff, but I wonder if you could speak to like how Einstein conceptualized it. Like, is space-time a real and physical quantity insofar as it is, measurable and tangible in some sense, or is it a mostly mathematical or construct?
I seem to recall some quote from Einstein somewhere where he basically wrote something to the effect that basically his theory of relativity replaced ether by space-time in a way. So I guess that if I remember, if I even remember this quote correctly, that would kind of point towards that he kind of thought of it a bit as a material thing in some way, I guess, but also, yeah, I don't really want to put words in his mouth, so yeah, I'm not sure. I mean, my personal opinion, at least, is that I guess many of the misunderstandings between, I guess, flat earthers and other science skeptics and people like that kind of seem to stem from taking scientific theories like too literally, like they were like statements about some material reality. And so basically because of that, I kind of drifted towards the position that you shouldn't really take any scientific theory as a statement, like as an ontological statement about something that really is. I would just interpret those theories as this is a mathematical description of reality. If we translate what we measure in reality into some concepts in this particular way, and then do maths on it in this particular way and get results, this will tell us what we can expect in reality under some particular conditions. But that's pretty much it. I mean, I wouldn't take just because we get correct. Sorry. Yeah. Just because we get correct predictions and they are very accurate doesn't really mean that the mathematical model is anywhere close to material reality, right? So I would, yeah, that would basically be my position. But yeah, that's just
I'd argue that it's actually the flat earthers that are committing the reification fallacy in this case.
Often,
it's
yeah.
They think that just because Einstein used a mathematical description that uses terms such as space-time, that therefore space-time is the ultimate be-all and end-all. Whereas all we're saying is that this mathematical model seems to match with observations to the point that we can measure. So we just use it as a practical point of convenience. But whether that's actually what's happening underneath, that's kind of a philosophical question at that point. It's sort of analogous to the interpretation of quantum mechanics. Quantum mechanics is a series of equations that seems to work, and whether it is the Copenhagen interpretation or the Muddy Worlds interpretation, whatever you want it to be, that's kind of up to you. That's your sort of mental model, what's happening underneath. But the equations work nonetheless. They are independent of what you think is happening on the fundamental level, I guess.
Yeah, I agree.
So I quite easily can conceive of GR being explainable as a series of quantum mechanical interactions using particles that just replicate all the effects that GR uses space-time as a term to describe. You know, whatever. Pick whichever representation you like and
or something
run with
even
it.
different.
But the math still works.
Or space-time somehow being quantized and then particles being, I don't know, some particular interactions of space-time or whatever. I mean, there are many possibilities,
sure.
but that's all beyond me, really. I
would argue that it's kind of similar to the description of you can take the quantum mechanical interpretation of electromagnetics, or rather just a simple straight up electromagnetic field interpretation. Like there is an electromagnetic field that oscillates, yada yada yada, whatever, right? So you interact with the field. Or you can take the quantum mechanical particle interpretation and say that particles are exchanging virtual photons. Those are causing all the effects of electromagnetic interactions. Whichever one you prefer, the math works out the same at the end of the day.
Well, that's the thing I was trying to tell Winston in our debate earlier too, yesterday, was I was like, you know, you want aether to be this gravitational theory, and then you were talking about like the conceptualization of Newton's etheric notion of gravity. In what way is that going to be different from space-time? Functionally, right?
Can you repeat the beginning of the question? I didn't quite get that.
Yeah, so basically, Whitsitt was arguing that Newton had a theory of gravity based on aether, and that there's like this, you know, aether effect, and therefore like you can't have like Newtonian mechanics with space-time because space-time and relativity rejects an ether. But what I was asking Whitsitt was, okay, but what is the actual constructive definition of ether? And yeah, that's that. He couldn't really answer that too well.
Yeah, I think at the very least, usually the proponents of Ether like also are like
You almost had a coherent thought there.
also support the I guess the Galilean transformation, so they would kind of like to stick to the pre-relativistic world, which means that their ether would have a bit of different symmetries than space-time in relativity. So we would basically have something that still exhibits the same symmetries as Galilean space-time, let's say. But in relativity, we have this Lorentz symmetry, right? So this is quite different. And actually, Clive Wells made a good point in the chat on my channel that relativity seems to be essential for the spin statistics theorem, which is basically that like integer spin particles are bosons and half integer spin particles are fermions, and they behave different statistically, right? So like bosons can occupy the same quantum state, fermions cannot, for example. So, and that, yeah, I don't remember the exact derivation of the theorem, but I do remember that it did actually have something to do with relativity. Actually, relativity has quite a lot of. So, for example, okay, usually, so in quantum physics, usually stuff like polarization is related to the spin of particles somehow. So photons are actually spin 1 particles, which means that technically you should expect to have 3 different possible values of projection of their spin on some particular axis, like +1, 0, and -1. So that would actually correspond then to 3 polarizations of light, but we know that there are 2 polarizations of light. So what's happening there? And then it turns out that actually because of Lorentz invariance, so because the spacetime has this Lorentz symmetry and not like Galilean, it turns out that it is impossible for a photon to have this 0 state. So it's reduced to +1 and -1, and suddenly we get like those 2 polarizations instead of 3. So the very fact that we have like light that can be polarized in 2 orthogonal ways is also related to relativity.
Okay. And spin, I think, is a good example of what we were talking about before, where a mathematical model isn't really exactly what's happening, because the idea of a particle, which is like infinitesimal spinning, is not really well defined, but spin nonetheless is an important measurement because it describes how particles and atoms process, right?
Yeah, so
also the behavior.
Sorry.
Also the behavior of spin having to do a 720-degree rotation to return to the original spin, like that really bends the mind.
Yeah, I mean, so spin is not actually about spinning, but that's about as much as I'm able to say about this. So yeah, it kind of has some of similar properties to like angular momentum, which I guess is maybe where the name comes from, but that's kind of where the similarities end. And it's not actually about the point particles spinning, but yeah, more about some kind of symmetries, I guess. But yeah, this half spin where the symmetry is actually after 2 full rotations and not a single one, that's kind of interesting.
That thing absolutely is counterintuitive to me so much.
I actually saw a video somewhere that made a physical realization of something. I don't remember.
Yes.
But basically,
I might have seen the same video. It's about an hour-long presentation. I'm always reminded of a quote that was from one of the books that was the source for that presentation, which says basically that although the mathematics and algebra of spinners is generally understood, there's nobody really on Earth that can intuitively grasp what they are.
Yeah. No, I think I saw something shorter, like basically it was something about, I guess, if you have a cube with something attached to it, if you kind of rotate it 360 degrees, then it gets very tangled. But then if you rotate it 720 degrees, then you can do something and then it gets untangled, something like that. I don't remember the details, unfortunately.
Yeah, isn't that the Dirac equations or something?
No, Dirac is something different.
No, it's like you have a belt, right? And you can basically rotate in a way that does exactly what you just
I
said.
think I think you're thinking about a Mobius strip.
Oh, thank you. Yeah.
This is what I'm talking about. I've posted a chat here, or I could put it in the other channel as well. And yeah, it starts out, of course, with that cube presentation with the tangle up wires, or in this case, they're using a ball. But yeah, I know exactly what you mean.
Oh wait.
Yeah, he does, right? He said the actual name of it, right?
Oh, nice. Huh, I didn't know that the voice chats have their dedicated chat channels like text chats. I thought that this
Yeah.
was just the I thought that this chat was just the live debate text, but it wasn't. Okay.
Is that good or bad? Be honest.
I don't know. It's interesting.
Oof. Oh, do we have any other questions? Oh yeah. This is maybe getting more to GR, I guess, too. So I'll wait for that question till next time, actually. Then.
All right.
Oh, when we talk about length contraction, there's some idea that it's impossible to actually measure length contraction. Could you give some context on that as well?
No, I mean, I guess if you had a way of measuring, I guess okay. For example, you could devise a method of measuring the length of an object by, I don't know, bouncing light off both ends of the object, and then based on difference in time it took for the light to bounce back, stuff like this, you could figure out the length. I mean, if you had a method that in principle has to yield the exact distance between like simultaneous between 2 points taken simultaneously, and then you employed that to measure the distance between 2 ends of an object, and then you put that object in motion and use that method again to measure the distance at some moment between 2 ends of this object, you would get a different result. You would get a shorter distance. So in this way, this is actually like a physical effect that is measurable. I think what might be meant was that it turns out that if you look at an object in motion, that's not like one-dimensional or two-dimensional, but that is actually some three-dimensional object, and it's moving at some speed like in front of you. If you look at it, then it won't appear shorter to you, but it will appear rotated actually, because also of the difference in time the light must take to reach your eyes from like the back and the front of the object, as well as from the sides and stuff like this. So then if you do the math, it turns out that it will look like it was rotated instead of shortened. But I guess maybe that's what was meant when yeah.
Terral rotations. Yeah. And also, yeah, the actual visual effect when the object's approaching you, it'll look longer, and then on the way out it'll shorten it. Yeah.
I think the opposite, but yeah, but basically something like that.
Or is it? I don't recall anymore. Yeah. No. Yeah, it looks weird. I've seen some simulations of it.
Yeah, there are simulations of this. There are some nice like there was even a game that could simulate I think it was something like a slower speed of light or something like that, but basically you could see what happens if you move at speeds close to speed of light, and how the world looks then, and it was weird. Basically, if you move fast enough, you start seeing stuff that is actually behind you, because when you transform the speed of when you consider the light rays that reach you from behind and you transform their velocity to your reference frame, then they start basically coming from the front instead of from the back. It's a bit weird.
Yeah, they get rotated.
So basically, as you're moving faster and faster, your field of view gets compressed in front of you.
Yeah, that was a very nice animation of you like flying through like a cube matrix, and you could see that basically stuff was sort of blooming out from the center and disappearing towards the edges of your field of vision, even though that was basically already behind you.
So actually that gave me an idea, so just a moment, because I can show you something while I'm still presenting. I wonder what it will look like here. Just a moment, where do I have this? Okay, I wonder if this still works. Oops, nope. Huh, okay. That's weird.
Yo.
Doesn't this work? Yeah, I'll keep looking, but if you guys want to discuss something, feel free.
Another one that
I'll
other
talk, bro.
blurb I get is around
I'll
time
talk.
dilation.
You cut me off, dude. Time dilation. Go ahead.
Yeah,
Time
sorry, I was
dilation.
experiencing
Okay.
time dilation, and that's
So
why I cut
time
you off.
dilation makes Earth a blue marble. Okay, go ahead, bro.
Well, the one thing I get a lot with the Dirt Crew is well, time isn't actually real. You can't like manipulate time. You can't
Yeah, you
dilate
can.
time.
Shut up, dude.
Cesium atoms are just,
the speed of light. The terror
there's
of
no
ancient
time
Greek-
particle, they said.
Oh, it worked. Yeah, I don't know really what to say to that. I mean, you can measure time, right? Maybe you can't manipulate time in the way you cannot travel backwards and forwards as you wish, but you can still measure it. You can measure time between events. So, yeah, saying that it's not real, I mean, at the very least, you would have to, if you want to describe reality without using time, you would have to replace it with some underlying mechanism that then creates an illusion of time. But yeah, just saying that it doesn't exist doesn't really mean anything. Oh
Yeah.
okay. Yep. Now I have. Perfect. That's what I was looking for. You probably see this now. Yep.
Yep.
So this is a simulator that I created like a long time ago. It's not perfect. Like if I rotate here, you will see that there is like weird strip here because I never quite figured out how to interpolate some data well. So this tries to simulate lensing of light around a black hole. So this here is a black hole. And we can see what's happening to the image of. This is actually a picture of the night sky from Earth. That's everywhere here, and it's distorted by this black hole. But anyway, how did this all work? Okay, now we're moving, and we're starting to fall into the black hole. But what I wanted to show you is, now I need to remember. Oh yeah, that was the control. So I just accelerated forwards, and it compressed the field of view. And also these weird colors are basically Doppler shift. So everything is red shifted in the back and blue shifted in the front, and this white is basically UV. So we can...
Well, that's crazy.
Yeah. Wait. Okay, let's... Yeah. So if we go like here... Okay, oops, nope. That's too much. I don't remember the controls anymore. That was a while ago when I wrote this. Okay, but what I wanted to show you is what happens when we get closer. Oh, time warp. Okay, that's why this goes so fast. Okay. I forgot that this had this option. Yep, so we're getting closer and closer. Wait, I'll pause for a moment. So you can see in the bottom here, there is this our speed relative to the black hole right now. So we're going at half the speed of light. And this is the distance. RS is Schwarzschild radius, so the radius of the event horizon. So we're at the distance of just 2.7 Schwarzschild radii from the center in a way, because that doesn't really make much sense, but never mind. Anyway, once this falls below 1, we are below the event horizon, and then we cannot escape. But as long as it's over 1, we can still escape theoretically. But what I want to do is not to escape.
Although crucially, there's no stable orbits below a certain value above 1.
Yeah, I think it was like 3, I believe, if I remember
Something
correctly.
like that.
What did you use to make the simulation? This is super cool.
This is just C++ and OpenGL.
Oh wow, Chad.
I have the source code is on GitHub somewhere. I can send it to you later.
Yeah, that'd be awesome.
Sealine, are you familiar with Space Engine?
I think we just crossed the photon sphere, so that's why. Yeah, 1.5 is the photon sphere, so at that point the black hole will cover half the field of view. Okay, yep, and we're starting to fall, and okay, that doesn't look good. Okay, we'll be falling. So I just employed time warp. It's like 3% passage of time, because yeah, I won't be able to get us out of here now. So yep, and now we are below the event horizon. So speed relative to the black hole no longer makes sense, because once you are below the event horizon, speed, time and space kind of switch places in a sense. Maybe it's not the best way of describing that, but it really makes no sense to describe speed relative to the black hole anymore.
All paths lead to the singularity.
Yeah, so the singularity is at 0, so I don't remember what will happen then. I think the simulation will just stop. So as we approach, now funny things, as you can see, I'll slow this down a lot to take a look. So funny things happen to the field of view as well, as you can see. So this is distorted quite a lot, and it's slowly getting compressed into like a thin band here. But yeah, let's accelerate this again and start falling. So yeah, we get closer and closer and closer. Okay, I'm slowing down that time a lot, because if I didn't, we would have already been at singularity for a long time. Okay, yeah, okay, and it broke.
Somebody said singularity?
Yeah, I mean we're almost okay, yep, it broke.
Yeah, that's the heliocentrist worst nightmare, right? So
yeah,
you're really going on you're stepping on mines right now.
Sorry, was that to me or to?
Yeah, like
that was to you.
Ignore the dude.
You, right?
Okay.
So no, don't ignore me, right? Tutorial, like shut up. Anyways, so yeah.
So Sealine, if you're from, have you heard of Space Engine?
Yes.
Oh yeah, me too.
Yeah, Space Engine also has a simulation of roughly what it would look like falling into a black hole. I don't think they cover the wavelength shifts, so it's mostly just gravitational lensing that they focus on.
Yeah, this here is kind of very rudimentary, like Doppler shift, because you can't really compute Doppler shift well without assuming some sort of a spectrum for everything. So I didn't have spectra of all the pixels full spectra of all the pixels in the image. So I just assumed some spectrum corresponding to red, green, and blue, shifted that and summed this, and this is what came out. So this definitely isn't what this would actually look like if you were falling into a black hole, but it gives you some idea.
Well, I mean, you get shifting into the infrared radio, and then the opposite way around into ultraviolet stuff you wouldn't be able to see. So
hard gamma
you
at some
definitely
point,
would not get a. Yeah, you definitely would not get such a nice picture.
Yeah, so this black and white part that was supposed to be ultraviolet and above, right? So everything that got shifted like outside of the visual range, you would have to have like a very specialized equipment to see something like that. Although one thing that this does not simulate, and there is an effect, it's called beaming. So basically because of this compression of stuff in front of you in the field of view, it would also get much brighter, and I don't simulate this change in brightness.
Oh yeah, it would get blindingly bright.
Yes.
So let me fire up Space Engine here to show you what they do.
Okay, I can stop sharing my screen.
Fucking space-time is so hot, dude. So hot, dude.
But is it hotter than Hansel? That's the real question.
So this is Cygnus X1, everybody's favorite. And that's what they do.
Nice. Oh, that's pretty cool.
It does get slower when you get very, very close to it, but they do show things like you would be able to see the far side of the accretion disk, even when looking side on, because of the disturbances there, and it lenses the entire universe around it. Of course, if you look at the actual, where's the stellar magnitude? It would be actually absolutely blinding to be this close.
Apparent magnitude minus 55. Yep, that's
Yeah, that would cook
orders
your
of magnitude
retinas.
brighter than the sun.
It's like 20 orders of magnitude brighter than being close to the sun.
So the sun is like minus 26. So let's say this is 30 magnitudes more. So 30 magnitudes divided by 5, that's 6. So 100 to the 6th power. So like a billion, trillion times brighter, something like that. Yeah.
Yeah. I mean, it shows it when you're far away, it sort of tries its best to show the fact that, it's actually a blinding star.
Yeah.
That's next to a blue supergiant, but
yeah, that's cool.
They try and help you out, so to speak, when you get very, very close, so that you would be actually able to resolve something in there in the actual image. So what would it do? Yeah.
Ouch.
This is if I switch off HDR, high dynamic range, and just let the thing behave as if you were in a camera that had, I don't know, however many millions of f-stops probably to get the thing looking right, correctly exposed.
Not to mention it would have to be made out of something probably more durable than tungsten even.
Probably. I mean, yeah. Anyway, if I go back into...
Okay, what's the...
And I can slow down time.
Oh, it stopped showing apparent magnitude. Oh.
Yeah, it gets blown out past a certain level. But yeah, this is sitting right over the event horizon, and I've slowed down time by a factor of like 10,000 at this 1,000 at this point.
Yeah.
But crucially, and by the way, look at this when I'm moving in and out, it shows the speed of light effect.
Yeah,
so as I'm moving in at faster than the speed of light here, or very close to the speed of light, I'm moving faster than the local speed of light with this time with the slowing time effect. So if I'm going at this speed backwards, at this point I would be moving at like, I don't know, 100 times the speed of light. So I'm moving backwards in time.
Yeah, that's nice.
And they show this effect for neutron stars as well. Space Engine is really cool in that it shows a plausible simulation of what stuff would look like. So we don't have obviously telescope data to fill this part in, but we have reasonable data to assume what it's probably going to look like. Yeah, blue luminous supergiant is the Cygnus pair. And of course we can go to Sagittarius A star.
The black hole in the middle of our galaxy.
Yep, that's a big boy. That one, even if I don't slow it down, this is at real time, and I'm currently at a distance. of 31 astronomical units, and that's already how big the thing looks. So at this point, I'm like at the orbit of Pluto, and it's already distorting the night sky.
Whoa.
So yeah.
That shit's great.
Yeah, that's cool.
At a distance of what let's see, distance. This is about what it would look like at the distance of the Earth from the Sun. The universe would look very strange.
Yeah.
It'd probably be all dead by tidal forces, but that's kind of a little detail. Anyway, neat little effect. Once again, I'm moving at many times the speed of light, so these effects are me going forward and backwards in time, so to speak. And what you can do is there's a way to display orbits on here. Where is it? Show orbits.
Oh, wow. That's cool.
And those are all the stars that are orbiting the thing. So what I can do is even if I turn the orbits off, I go ahead and time accelerate by a quite significant factor. You can see the individual stars orbiting the thing. And here's the passage of time. So a year 2030, 31, 32. But yeah, on a span of a few years, these guys are whizzing about.
And those are pretty big orbits, I think.
Yeah, absolutely. Let me, how's it like this guy here? He has an orbital period. Does it say, yeah, orbital period of 11.5 years.
Yes.
A semi-major axis, 829 astronomical units.
Yeah.
But let's check this out. This guy gets close in. This guy here. So he is currently going, does it give me a speed? There used to be a way to get information about the object here. It's a real object, and I want to look at that's this object properties. I was looking for the velocity. It would probably go a few thousand kilometers per second in this part of the orbit.
Yeah, I'd expect so.
I don't know. Whatever. I have to look at the data, but yeah, it's going at a pretty good clip. Yeah. I've kind of slowed down time again. Anyway, fun stuff. Space engine.
Coolio.
Yeah, and Space Engine employs a probabilistic generation model. So you can go to anything you see in the night sky. So at this point, I'm in intergalactic space, so I can just go ahead and point at something. Say that's a galaxy that's actually from the New Galactic Catalog. So that's a real object at a distance of 77 million light years. And I can just go that away. And obviously, we do not have the stellar data for the individual stars inside, but I can just go ahead and zoom in, and Space Engine is going to start generating stars.
Yeah,
that are
is he still in
plausibly.
here? Hold on, dude. You wait.
So yeah.
But yeah. So
Space Engine is a cool little game on Steam.
Silence It Out is like 10 times smarter than you. Would you agree? Yes or no?
I would agree with that statement as it pertains to me. Yes.
1,000 times smarter than me.
Yeah. Whatever.
What was the purpose of the question?
I mean, the ultimate
You
goal
act
is
like there's a purpose to his geometric Brownian motion of speech.
That's true. That's true.
Right, well,
Point taken.
Yeah. So so I'll cut to the chase, right? you're a blue marble earther.
Yes. Whatever the fuck that.
Wait, who said yes? I know Prime did, right? So yeah, dumb fuck. Okay. Well, who else? Not looking good.
I know.
All right. Anyway, I think I'll be finishing for today. So, like, thanks again for listening and for questions and for the chat afterwards.
Thanks. I can't wait to take a stab at the generalized theory, because that one bends my mind.
Yeah, we'll have to schedule
yeah.
some further presentations or something.
Yeah, I hope you recorded his presentation, right? I hope you recorded it and you play it at 0.25, right?
Yeah, I was
slow.
streaming it, so this will be on my channel. At least it should be.
Cool.
Yeah, so not sure when I'll be able to kind of prepare a second part, but yeah, if you guys found that interesting, then definitely I would love to do so.
Yeah,
cool.
That would be freaking awesome.
Definitely come to that.
Awesome.
Yeah.
All right.
Yeah, you know how somebody throws a.
All right, thanks, man. Take
line,
it easy.
Right? Somebody throws a fish line, right? So you're waiting for a fish, right? So you're the fish, right? You need help.
All right, thanks, Science It Out.
Okay, I can be a fish. Okay, thanks, guys. Okay, see you another time.
See ya.
Bye.
All right. Yeah, so I'm still streaming, right? I think so. Oh, oops, what's this? Okay. Oh, yeah. All right. Right. Let me just do this. Oops. Yeah. Right. So yeah. So to you guys who were here in the on my channel in the live stream and not on Discord, also thank you so much for watching. Yeah, I wasn't very active in the chat here. I did see some comments in real time because I was trying to keep it in view, but I might have missed some things. Yeah, so Mike didn't quite miss everything because he was present on Discord. So I think he was watching there. But yeah, thanks again for your attention, for watching this. I hope you will tell me in the comments if this was interesting. I would love to hear what you thought of that. From what I see, I guess it wasn't too bad, so that's good to know. Oh, hi Ian. Yeah, sure. Feel free to check it out whenever you want. I mean, I'll probably have to put in the description when the actual presentation ends because it didn't last until the end. There was a lot of chat afterwards. But yeah, okay, yeah. Yeah, I think I said what I want to say. So yeah, thanks guys again, and yeah, there might be a part 2. If there is, I'll definitely put up a stream again and see you there possibly. Or if not there, then maybe I will upload something else. I mean, everything is possible. So yeah, see you next time or on Discord or something. Thanks. Bye bye.